Hi guys, welcome to the next coding pill. Look at these beautiful glowing color clouds. They are called heat maps, and in this video I'm going to show you how you can code them yourself and place them on any real-world map you wish. I'll guide you through the math and how we can color each pixel. Oh, and here's the fun part. We are doing everything from scratch, so no libraries, no frameworks, just pure coding. Oh, and by the way, you can find the code below in the description. Just feel free to download it, open up directly in your browser and play around with it. I would love to hear what you think, so leave it in the comments. And here's something cool. In the 1880s, the French painter named Georges Seurat had this crazy idea. Instead of mixing colors on his palette, he just painted with thousands of tiny dots on his canvas. Up close, it looked like a mess. But stepping back, and your brain could assemble the whole dot mess into a picture. And that's exactly what heat maps do. Up close, you've got thousands of points. But stepping back, the whole picture appears. Except we are not stepping back with our eyes. We are stepping back with math. And today we are going to build that math. So I got hooked with heat maps. Not the install a plugin and call it a day kind. I really wanted to understand the algorithm behind it. I really wanted to understand how every pixel gets its color. It's like, I don't know, buying a cake versus baking one on your own. You can do both ways. Both ways have the same result, but only one way teaches you something. So I built it. By the end of this, you know exactly how heat maps work under the hood, how to implement the algorithm yourself, and how to draw it on real maps. However, there's a catch though. When I put my approach on actual maps, something was off. But we come to that later. Alright, let's get started. Heat maps are just a tool to unravel the chaos that lies in the data underneath. And what we often encounter is we have thousands of data points, maybe millions. And here's the thing, your brain is incredible at recognizing patterns, but only if you present it the right way. A cloud of 10,000 scattered coordinates, your eyes glaze over, you see noise. But take the same coordinates, run them through an algorithm and suddenly structure appears. Hotspots, clusters, cold zones. Patterns that were invisible a second ago. That smooth surface, that's the heat map. And they appear everywhere in our daily life. And they all work the same way under the hood. Scattered points go in, a continuous density surface comes out. Areas with lots of points glow hot, sparse areas stay cool. That's the whole idea. So let's get our hands dirty. Time for some theoretical background now, but I promise you it's going to be super fun. How do we get the colors from the scattered points? The algorithm has a fancy name. It's called kernel density estimation, or KDE for short. I mean, it's one algorithm you can use, but I prefer this one. Stick with me here on that. This is the part that makes the whole video click. But let's slow down for a second. Forget about maps. Let's check out data in one dimension first. Say you've got a couple of measurements, just numbers on a line, and you want to find the areas of high density. Think of it for a second. How would you do it spontaneously? You could start with histogram. Chop the lines into bins and count how many points fall in each line. Histograms are nice because they provide a fast way to visualize your probability distribution. But here's the issue. Move the bin edges slightly and the histogram looks completely different. The shape depends on where you drew the lines, not on the data itself, and that's ugly. Furthermore, they are discrete, and sometimes it is useful to have a smooth estimation of the underlying probability density function at hand. To understand kernel density estimation better, imagine the following. Imagine each data point is a tiny candle. It doesn't just illuminate the exact spot where it sits, it casts a soft glow in all directions. Now, put 5 candles on a table. Where many candles cluster together, the glow is brightest. That smooth combined glow, that's your density estimation. Let's apply this idea to our data now, shall we? Look at that. No bins, no arbitrary edges, just a smooth curve that follows the data. But how is this done? Each data point has its own little glow radiating around. In this case, we put a little Gaussian function over each data point. Later, we will call this function the kernel. Remember, kernel density estimation, huh? But as an intuition, just think of it as a candle glow. Areas with more data points have overlapping Gaussians. These are considered dense areas by definition, of course. And we receive the final KDE value, that smooth curve, by simply summing up the Gaussian overlaps. That's just it. That's the whole idea. And now we can adjust the degree of candle glow of how wide the influence of each point is reaching. Small glow, you see every individual point. Large glow, you overshoot all details. And yeah, somewhere in between you find your sweet spot. This glow is called the bandwidth of our kernel density estimation. Okay. Now that you have the idea in your head, let's jump right into the formula. Don't worry, I'll explain everything in detail. You have seen everything already, we're just formalizing things now. F hat of x is just our KDE value at any given point x. High value means bright color. Low value means dark color in our heat map. Let's break the rest down. N, that's the number of your data points. So for example, you've got 100 earthquake locations. Yeah, then N is 100. K, the kernel function. That's the shape of your candle glow. We are using the Gaussian here, the bell curve. Yeah, remember, we have talked about it in the one-dimensional case. It peaks at the center and fades smoothly towards 0. So don't get too confused with the kernel. Just accept it as the shape of our candle glow, but don't get too confused with it. X. X is our input, a fixed position, which gets compared to any data point that we have. Xi, we are iterating each individual data point we have measured and the position of, for example, earthquake number I. And then we have H, the bandwidth. This is the big one. It controls how wide each bell spreads. You've seen it earlier. Small h, tight spiky bumps. Large h, broad smooth blobs. And here's the kicker. For a large dataset, the kernel shape barely matters. You have several options here, but for my experiments, it didn't really matter dramatically. Gaussian, Epanenchnikov, or even box kernel. It's the bandwidth that makes or breaks your output. Theory is nice, but you know what's better? Seeing it all come together in front of us. So I built a JavaScript application that runs entirely in a browser. Just a canvas, a grid, and a KDE formula from last chapter. Think of it like a chessboard. Each square on the board is a cell. And for every cell, we ask one question. How much density is here? We sum up the kernel contributions from every data point, and that sum becomes the cell's value. High value, hot color, low value, cool color. You know how it goes. Here's how it works under the hood. We set up a 2D array, that's our grid. Then we loop over each cell, and for each one we calculate the KDE value by summing up the Gaussian contributions from all data points that we have. The closer a data point is to the cell center, the more it contributes. And then we map these density values to colors. Look at that! Now here's where it gets fun. I added some sliders to adjust several parameters, for example the bandwidth slider. Keep it small and a heat map gets spiky. Each data point creates a tiny isolated hotspot. Set it high and everything blurs together into one smooth blobbly. Same data, widely different picture. We can also adjust the bandwidths for X and Y axis independently since we are in 2D now. Grid resolution. Fewer cells means faster but chunkier. More cells means finer detail but more computation, and you can see the trade-off live. And then there's color. I implemented several scientific color palettes like Inferno, Viridis, Magma, Plasma, and so on. They also work if you're colorblind. The grid playground is fun to experiment with, but we are not here to color abstract squares. We want to color real streets, real cities, real geography. And this is what we're going to do next. Let's start with the real world maps. The stack is really simple. Leaflet for the interactive map and OpenStreetMap for the data tiles. Both free, both open source. Oh, and by the way, Google Maps has deprecated their heat map layer in 2025, so if you were using that, you need an alternative anyway. So what we're doing next is basically placing a transparent sheet of grid paper over a real map. Each cell on that grid gets a color based on the KDE value at that location. The map shows through the transparent parts. The hotspot glow on top. Here's the approach. We take geographic coordinates, latitude and longitude, and convert them to pixel positions on the leaflet map. Then we lay over our KDE grid over those pixel positions, compute the density at each cell, and render it as a semi-transparent canvas overlay on top of that map tiles. So to summarize, we walk through three different spaces. First, the geospace where we have latitude and longitude. Then we have the pixel space, that is the position in the leaflet viewport. And then we map that to the exact cell of our KDE grid. And this is our way. All right, we have built the engine. Time to feed it with real world data to see what happens. You know, the internet can be a great place. Forget about X or Instagram and all those senseless discussions there. It's so much more. You can find so many great geodatasets on the internet that awesome people have put public, so we can use it now and play around with it. We start with GPS trajectories I downloaded from Kaggle and Microsoft directly. Here you can see taxi movement across the city of Porto and a GPS tracking of users in Beijing. Just relax and enjoy the pure aesthetics. The next dataset comprises earthquake data. The USGS, the United States Geological Survey, publishes their entire earthquake catalog as downloadable CSVs. Latitude, longitude, magnitude, depth, timestamp, you name it. Decades of seismic events free to grab. And there it is. Look at that. Earthquakes are often caused by tectonic plate movement. What I find stunning is that we can clearly see the boundaries of those plates on our map, colored by the heat maps. For example, the boundaries of the Philippine plate is standing out. Isn't that fantastic? The data is telling us a story. Everything seems to work now, but something is off. I look closer at the density near the poles versus near the equator, and the former one seemed somehow inflated. Areas near Scandinavia and Alaska were glowing hotter than they should. The data didn't support it, so what happens here? A little research opened my eyes. The Mercator projection. Imagine you take an orange and you peel it, and now you want to put the skin completely flat on the table. It doesn't really work, right? It tears and stretches. And for Earth, it's the same. It's a sphere, but maps are flat. So to make a flat map, we have to stretch and squeeze parts of the Earth to make it fit. The Mercator projection is one way of doing that. It's the classical map you've probably seen in school, the rectangular one. But here's the thing, it lies a little. Maybe you heard about it. Countries near the top and bottom of the map, near the north and south poles, look way bigger than they actually are. For example, Greenland looks as big as Africa at a Mercator map, but in reality Africa is 14 times bigger than Greenland. Countries near the middle, the equator, are shown more accurately. Google Maps, OpenStreetMaps, they all use Web Mercator. That's the standard projection for web maps. But here's the problem. My grid cells are uniform in pixel space, but in geographic space? No. A cell near the equator covers way more ground than a cell near the poles. Latitude and longitude are angles on a sphere. If you naively map them literally to grid pixels, you add unwanted distortion. Since heat maps visualize density, unequal cell areas mean distorted densities. Let's fix it. Thank God, no need to reinvent the wheel, because leaflet covers that already for us. So what lat-length2 container point does? It's a leaflet method that converts geographic coordinates into a pixel position as leaflet's math magic has already rendered it. The pixel position you get back already accounts for the projection distortion. Done. Same data, but now the density values mean what they are supposed to mean. I have to say, this was my biggest learning in this coding pill, and every problem you work on makes you a smarter person. So don't take the shortcut, dive deeper. Now, the visualization looks pretty good already, but once I started loading datasets with 100,000 points, my browser starts to sweat. Let's talk about making our approach faster. So 100 data points, instant running, none of a business. 10,000s, couple of seconds, but 100,000s, the tabs freeze, fans spin up. That's not ideal. So with increasing number of data points, my browser starts screaming for help. And as you know, JavaScript is not the fastest language out there. So let's fix that. Remember, for every single grid cell, we are summing up the kernel contribution from every data point. It's like asking every person in a stadium to shake hands with every other person. It scales badly. The biggest win is the simplest one. We skip data points that are too far away from the currently observed point. So what we do under the hood? For a certain cell, we stop considering the data points that are so far away that their influence of the total sum is negligible. The Gaussian bell from these points are almost hitting zero, so no influence at all. So we stop considering them. For each cell, we only look at the data points within 3 times age, which is 3 times the standard deviation. Everything else? Ignored. That alone dropped computation time dramatically. Instead of checking every point for every cell, you only check the nearest one. And with this improvement, I can render continental-wide heat maps without any hardcore map freezes. I was also thinking, is there a way to find the best bandwidth for any given map viewport that we have? And yeah, there is, theoretically. There is Silverman's rule of thumb. It uses your data's standard deviation and sample size to pick a reasonable age. But my honest feedback, in my experiments, it did not work well. I am pretty sure it's because Silverman's rule of thumb assumes the data to be normally distributed, which is not the case for my geodata. So for my heat maps, I rather tuned that parameter manually. That's it. We did it. We built our own heat map framework from scratch. Scattered points in, heat map story out. And I have to say, it doesn't look too bad and works pretty solid. If you really want to understand the tools that you're using, not just use them, but really understand them, feel free to subscribe. This is what this channel is all about. And if you have any idea what we can do next, I'm more than happy to read from you in the comments. Next up, I'm thinking about taking this into 3 dimensions. Maybe time as a third axis, temporal heat maps. We'll see. Until then, thanks for watching.